Alright, let's take a look at an example of, you could look at this as a mass on a frictionless surface or an inclined plane with no friction, or in this case it's a runaway car. This is from my Survey and Jewett text. It's a pretty good example. Well, what we need to do is make a free body diagram. We can do this directly on it. On the inclined plane problems, I like to do it directly on it, I said, just because I can get the lines parallel and perpendicular a little easier. So let's say it's starting at rest, it's at some angle theta, and it's some mass m. I'm going to do this one in all letters, and then we can plug in some numbers and see what happens. But you got to get good at just using letters too, the variables. First things first, free body diagram, and then apply Newton's second law. So what do we got here? I'm going to draw the mass pointed straight down times gravity. And let's go ahead and break that up into parallel and perpendicular components, which make a right triangle. Now, this angle becomes this angle theta right here, not this one. So if you do SOHCAHTOA, we get mg cosine theta for the perpendicular component and mg sine theta for the parallel component. Alright, we have, so that's two forces, right? One in the parallel and one in perpendicular. We would also have a normal force pointed up. That would be, if it's not moving up or down off the surface or accelerating, then this would be equal to this. We don't have friction in the problem, so we're not going to be dealing with normal force. We can go ahead and practice summing the forces though. So if I summed the force, let's call the perpendicular direction, we have that normal force, it's positive, and then we have a downward pointing mg cosine theta. That's equal to the mass times the acceleration in the perpendicular direction, but it doesn't come off the surface, so there's definitely no acceleration in the perpendicular direction. That leaves us with the normal force minus the component of the weight in the perpendicular direction equals 0. This is an example of Newton's third law. We don't necessarily apply the formula, right? That's what I mentioned before. It ends up popping out, or we use it as intuition to solve the problem. Like, we need to know it and understand it so we can visualize that these are equal. What do we get mathematically? We get that the normal force is equal to that vector. So that's not what we're looking for. I want to know the acceleration. What's the acceleration? Then we can look at what's the velocity after a certain amount of time, or any time t, and how far did it go after some amount of time t. Let's sum the forces in the parallel direction. In the parallel direction, I see this one right here. We can call that negative if we want, or we can go ahead and call down the plane positive. I like to call down the plane positive. That's about the only time I vary from my positive to the right and positive to the up direction. So what do we get? We sum the forces. There's only one, and it would be an mg sine theta. And that would be equal to the mass times the acceleration in the perpendicular direction. Now, if it's going down the hill, it's going to accelerate, and that's what we're looking for. So, cancel mass, we find out the mass doesn't matter. That's a fantastic thing. When things cancel, it's great, but it's pretty cool, right, to see that it doesn't matter how massive this thing is, or how large it is even. Eventually, wind resistance would slow something down, or impede its acceleration, but right? Like mass doesn't matter. That's a pretty cool thing. We can just solve this now. The acceleration in the perpendicular direction is equal to g sine theta. So it's only a function of theta, not a function of time or anything. So we can say, well, at 30 degrees, which is about what I drew this line at, we could say that it's equal to 9.81 times the sine of 30 degrees. The acceleration would be 4.905, not degrees, meters per second squared down the incline. So if we needed to put it in vector form, we know that it's some 30 degrees that direction. We can break that into components then. That's not what we want to know for this one. We actually want to figure out now maybe how far did it go? Or let's say how fast. What's its speed at some time t? Well, what we found was a constant acceleration. We found a acceleration down the plane of 4.905 meters per second squared. Since that's constant, we can use the constant acceleration kinematic equations. If I wanted to know the final velocity at some other time, then we use v final is equal to v naught plus the acceleration times time. Now we said it was from rest, so we can say that's equal to 0. And we get v final equal to that 4.905 times t. So let's say after 5 seconds. So I'm going to plug in 5 seconds. Seconds and one of those seconds will cancel and we'll end up with a velocity, meters per second, 4.905 times 5, and I get a velocity of 24.5 rounding up meters per second. Alright, well, what if we wanted to know how far it went? Or its position down the incline after some time t. Well, we use a constant kinematic equation again. In this case, we could use our, it's not really, I guess we could call this our x prime direction. You'll see some textbooks do that. So we can say that x prime is going to equal x for right now, and then use x final is equal to x initial plus the initial velocity times time plus 1/2 times the acceleration times time squared. Now this acceleration becomes that perpendicular acceleration that we found right here, and it was from rest, so v naught is equal to 0. That whole term goes away, and we want to know how far it made it from rest, so that initial position is also at 0. Those don't have to be, right? It could have had some initial velocity, and we can still plug in 5 seconds right there. But all we end up with in this case is that its final position relative to where it started is 1/2 times the parallel down the plane acceleration times t squared. So 1/2 times the 4.905 meters per second squared times 5 seconds again. And don't forget to square it. So I'm going to go ahead and square the 5 first. That's how I usually take care of this. And then multiply by 4.905. And then divide by 2. So I get that it made it down the incline 61.3 meters. And if you go ahead and say down the incline, that takes care of the direction for us. And that's it. the next step in this type of problem would be to say, let me draw a new one real quick. I need my ruler. The next step that we need to be prepared for is, if that car was just some mass, it is going to have some component of weight going down that we need to break into its components. So mg cosine theta, mg sine theta. We always have to do that. Okay, if we have an inclined plane on some angle theta, we got to break it up into components. We cannot add the vectors unless we do that. Okay, the next step would be, well, maybe what if a spring was pulling it up? That means it would be pulling it up that way. If the spring is compressed, it would be pushing this way. We're not going to do spring forces on this test. I'm just getting you ready for where we're headed. And then we're also possibly going to have frictional forces. If this was moving with some velocity in this direction, then friction would be slowing it down and moving it, or acting in the opposite direction. The reason we will need the normal force is because of our friction equation. You might remember it. It's the coefficient of friction times the normal force. So that's why we'll have to sum those perpendicular components. In this problem, we ended up finding A perpendicular. The acceleration was just equal to that component because it was frictionless. If we had friction, that would be acting in the opposite direction, slowing us down. If we had a spring acting in this direction, it would be speeding us up the incline. We could also apply a force that is not in line with its motion, like this. Alright, if that was the case, we would have to break it up into components perpendicular and parallel to the plane also. That's about it. I'll do some more examples for you coming up.